All right. So, welcome to Lecture 5 here of Introduction to Logic. Um, our plan for today is a little bit funny. So, what I want to start with is kind of going back over the stuff we finished the last lecture on and we talked a little bit about in the tutorials, because I want to make sure that we're all on the same page with regards to what happens when we have multi-place predicates, so relations, and we can quantify into the various places. I also want to briefly talk to you about Pokemon, but that's related, I promise. So I want to do that, and then I want to introduce to you the last little piece of machinery for FOL, which is our identity predicate. Identity is a special relation, but it's a relational predicate. So that's why we got to be clear about the relation stuff first. And then once we have the identity predicate, we'll put it to a bunch of uses. And what we're going to try and do today is teach you how to do at least one, at most one, and exactly one. So we'll talk more about that. Then we'll talk about definitions. This is basically another way to say exactly. And if we have time, if we have time, we'll define up the notion of FOL sentences. It's not the end of the world if we don't get to this. It's sort of aspirational. We're going to talk about more FOL stuff next week. So that's the plan. Cool? Okay. So, as I promised, let's start by talking about Pokemon. So, this was in the slides last week, but I want to make sure that we talk about it in the lectures. So we said when we're thinking about names in first order logic, names have to pick out at least one thing in the domain, right? We don't have any empty names. But something interesting is while names have to pick something out, we didn't say the same about predicates. That is, there's nothing preventing us from invoking predicates that don't apply to anything in the domain. So for example, if we took the domain of people that are in this room right now, if we use the predicate is outside the room, right, that's a predicate that doesn't apply to anything in the domain. To put some technical terms on it, we'll say a predicate that applies to nothing in the domain is empty. Now, empty predicates are kind of weird because we can use them for various things. And I want to give you an example of how we might use them. So let's take our domain to be people, right? And let's have the predicate P be is a Pokemon, and the predicate C be is cute. So with this kind of symbolization key, how would we express all Pokemon are cute? Well, if it's all, right, it's going to be the universal. But we don't want to say all with the conjunction. Right? It's almost always, if you have the universal, it's going to be linked up with the conditional. So this is going to be a way for us to say everything is such that if it's a Pokemon, then it's cute. That is, for all x, if px, then cx. Right? Again, this is that every F is G structure we talked about last lecture. Okay, so that's our first one. Now, how would we, again, using this key, express this sentence, some Pokemon is cute? If we hear some, we know that's always going to be the existential. Right? And if it's the existential, it's very likely to come along with a conjunction. So we're going to say, there's something in the domain that's a Pokemon and is cute. Problem. Now, getting ahead of ourselves a little bit, so we're going to talk about when FOL sentences are true and false next week. But just thinking about it for a second, on this symbolization key, is sentence 6 true or false? Is sentence 6 true or false? Is there at least one thing in the domain that's a Pokemon and cute? No, it's false, right? It's false. There's plenty of cute people. Insert your own examples here. No judgment. But unfortunately, Pokemon aren't people. So There's nothing that's both a Pokemon and is cute. Cool, so 6 is false. But what about 5? Is 5 true or false on this symbolization key? Yeah. We just want to know on this, is it true or false? That's the important thing. So maybe it's contingent or necessarily true. I just want to know, given this setup, true, false? Nice, nice, nice. So note the big structure inside the universal here is a conditional. And what happens with a conditional where the antecedent is false? What's the truth value of a conditional with a false antecedent? It's always true. It's always true. So what does this mean? It means that if you have a conditional whose antecedent is an empty predicate, that is, a predicate that applies to nothing in the domain, and that conditional is true. And that's really weird, because it's going to turn out that all Pokemon are cute. It's also going to turn out, given this setup, that all Pokemon are not cute. In fact, on this setup, it's going to turn out that all Pokemon are not Pokemon. Right? Because it doesn't matter. The antecedent is always false, because nothing in the domain satisfies the antecedent. So we can plug in anything you want as the consequence. The universal conditional is going to be true. So that's something a little weird. That's something a little weird. But this comes up. It's gonna be important next week, so it's worth mentioning it now. We can say when F is an empty predicate, then every sentence of the form like this, a universally quantified conditional where F features in the antecedent, is going to be vacuously true. That is, it's true just simply from nothing at all. So that's the first little bit I wanted to get before we go on. Empty predicates lead to vacuous truths when we're dealing with conditionals. Now, the second thing I want to talk to you about, unfortunately, we've got to leave the Pokemon behind, which hurts me. I want to talk to you about relations. Now, last week, we mostly talked about one-place predicates. Is a spy, is vegetarian, is a Pokemon. Predicates that have space for one term. But lots of predicates we'll be interested in are going to have multiple spaces. They're going to be relations. Is taller than, is poorer than, loves, hates, whatever you want. In these cases, there's always more than one space. Space for multiple names, or potentially for pronouns, quantifications. Now note, we're going to restrict ourselves just to two-place predicates. But we could theoretically keep going. We could have 3-place, we could have 4-place, you could have 84-place relations. Some really interesting networks will be characterized by those properties. But our interests just end at 2. That's enough for government work. Now, once we have multi-place predicates, we can say a lot more. So for example, we talked about this right at the end of lecture last week. We had a kind of symbolization key here, and we were talking about different ways you could fill in the gaps to get different relational expressions. And the way we do it, you write the relational predicate, and then whatever term you put just next to it, the first one along, occupies the space labeled with 1. Then the second one occupies the second space. So in this case, right, taking our first sentence, Finn occupies the lover position, and Princess Bubblegum occupies the beloved. Finn sort of sends the affection out, Princess Bubblegum takes the affection in this case. And again, it's important to note the order that we write things in, because it will say different things. LFB tells us Finn loves Bubblegum. LBF tells us Bubblegum loves Finn. Now, why does this matter? Well, one thing is that we can capture relations. That's really cool with names. But of course, if we have multi-spaces, that also means we can use multiple quantifiers. So we can start to talk about things like this. Here's a very simple, silly example, but it's worth practicing. We've got a symbolization key. Our domain is going to be people in anime. We've got one name, Nathan, little n. We have one place predicate is an anime. We have the two place predicate F, which is one is a fan of two. And we have another two place predicate, one is a friend of two. So using this key, how would we say Nathan is an anime fan? We can. Yes, we can. So let's think, what's in our domain? Our domain is people in anime, right? And if I say Nathan is an anime fan, what does there have to be? There has to be something in the domain that Nathan is a fan of and is an anime. Right? Do we hear it? So, how would we say there's something in the domain that Nathan's a fan of and is an anime? Well, we hear the something, right? It's going to be our existential. And then we just plug it in. There is something, it's an anime, and Nathan is a fan of that thing. Before we go on, so far so good? Do we see the structure here? Again, so in this case, the important thing, and this was the important thing, right? Our domain is people and anime. So we've got both of those in our kind of grab bag to pull out. Cool. Okay, so far so good. Now, how would I say someone is an anime fan? We've got it where it's me, but how would I say someone? Let's just think, right? We could take that same structure and let's just rip my name out and plug in an existentially quantified variable. That will give us a way to say it. Yeah, yes. It'll give us, we'll need two existential quantifiers. One of them will be our someone, and the other will be the anime that our someone is a fan of. We'll use that same structure we had for the top sentence. We're just going to kick the name out, replace it with an existentially quantified variable. So we can get something like that. A note, our existential why here is basically saying, hey, you can reach into the domain and find something that's a fan of anime. Now there is something, yes, yeah. In this case, it doesn't. And in fact, something really neat is if you have two of the same quantifier next to each other, it doesn't matter which one goes in front. The thing that matters is if they're different quantifiers. Then we cannot play swapsies. But it does matter here in the sense of which one we're attaching to the relevant gaps in the relation, right? It's important that our y needs to go in the first gap next to the f, because it's the thing that is a fan. And then our x is the thing our y is a fan of. It's much like the loving thing, right? Remember, if we wanted to say Finn loves Princess Bubblegum, F needs to go in the first spot, the lover spot, not the beloved spot. Yes? Absolutely. There doesn't have to be, right? I think we can think about this as, right, is a tennis player. Doesn't mean that you play in every single tennis game. So in order to really be something, to satisfy this kind of description, for our purposes, you only even need to do it once. I could be an anime fan if I'm just a filthy casual, and I only like Naruto or something like that. But of course, we all know that I am a straightforward otaku, so it's fine. I like lots of anime, but do I like all of it? Certainly not. So it's a weak claim in some sense. In order to satisfy it, we only need one. But that's really all the English says. It might kind of have an implicature of something stronger, but that's not strictly in the sentence itself. Question? Okay, so far so good? So, now let's do our third one. Our third one here. All of Nathan's friends are anime fans. All of Nathan's friends are anime fans. So first thing we can ask ourselves, how many different possible objects are involved? How many different potential different things are there? So we've got all, which we know what's all going to be. Always are universal, right? And then we've got Nathan, so we know my name's going to be in there too. So that's at least two things. But then we also know that there's going to be a third one. Why do we know there's going to be a third thing? Yeah, right? We've got the same structure that we've been talking about. And we know that when we talk about being an anime fan, that requires an existential to pull out the anime that our thing is a fan of. We're going to need at least three quantifiers, or three terms, better. One of them is going to be for all of my friends. One of these is going to be for me. You just use my name. And the last one is going to be for the anime that my friends are fans of. But note, does this sentence say that there is one anime that all of my friends are fans of? So we've got to be sure to put the existential inside the universal. So let's think about it. We can pull this apart. If it says all of Nathan's friends are anime fans, that should set off alarms because it sounds an awful lot like every F is G. In this case, the F is a friend of Nathan's. So we can say everyone who's a friend of Nathan is a fan of an anime. We can hear the every F is G structure that way, right? So we can basically say, cool, how do we do everyone who's a friend of Nathan? For all X, if X is a friend of Nathan's, then X is a fan of an anime. And how then do we do the consequent of this conditional? What's this bit gonna look like? Gonna look a hell of a lot like that, right? Just that we're gonna plug our X in as the fan, and our Y is going to be the anime X is a fan of. So we get this. What does this tell us? This says, hey, for everything in the domain, if X is a friend of mine, then there is some object in the domain that is an anime, and our X is a fan of it. Nice. So note what we did here. We started off with an easy kind of, well, sort of easy structure featuring a name, and then we quantified into it, and then we used it inside a bigger quantificational structure. If I ever give you stuff like this, I'll always build like this sort of way. Promise. Yes? So you could move this existential, if you want to, inside the universal, but it has to be inside, because otherwise it's telling us there's at least one anime, all of my friends. That's not what everybody should like Azumanga Daioh, but nope, not everybody does. Okay. Now, yeah. Good. So that's sort of what your man was just asking me. So importantly, if we put this existential all the way in the front, then we were saying there is an anime all of my friends are fans of. That's a bit like saying there's somebody every single person loves. That's not really what the sentence says, because what the sentence says is everyone who's a friend of mine likes some anime. Maybe a different one, but they like some of them. So if we move this up, it needs to still be inside the universal. The universal is the important one here. Okay. Yes, please. So you mean if we dropped the existential, not exactly what's written without the existential, would not have a, because we would just have X in there. Have a kind of proto sentence. Don't know what function we're supposed to in a name. Cool. Then we would have this. Whatever. Is an animated name. That would be fine. But if we have the variable there, it has to be attached to it. If it's not, we don't have a sentence yet. What we're going to talk about right at the end of the lecture. Cool, nice. Okay. So again, the things to notice here is we're just building on the stuff that we have before. We use the every FSG structure in the bottom here. We just allowed for, once we have relational predicates, more places to quantify into. Okay. So let's talk about identity. Identity is a special relational predicate. It's special in two different ways. We'll come to it in a second. But as a kind of run up to it, I want to tell you about why we need it. No, I flipped the order. Okay, let's start first with the general thought. Identity is a two-place predicate, but it's special. It's special in a grammatical sense, in that it is the only relation we write in between two terms. Like every other relation we write in front, followed by the two terms. This one we write in the middle. And it's also special in that we never have to specify what it is in any symbolization key. So to go back a couple slides, right? Note here we had to specify that F is a fan of relation and R is a friend of relation. We never have to specify with identity. If you use this symbol, it always represents identity. Grammatically special, and it's syntactically or even representationally special, lexically special, if you like. Now, there's some interesting philosophical questions about how to understand numerical identity, whether it means the same thing as is indistinguishable from, that is, has all and only the exact same properties. We are going to set that aside. What matters for us is when we see an identity claim, it's telling us that the thing picked out is the exact same object. That is, if you counted how many things you have there, you'd only have one. So Superman is Clark Kent. If we read the is here as expressing identity, tells us that, hey, Superman as a name and Clark Kent as a name refer to the same object. If I was to shake the things that are Superman and Clark Kent at you, I'd only be holding one guy. And you should be familiar with this sign. This is the same thing that we use in mathematics, right? When we say that two sides of an equation need to equal out, what we're basically saying is you've got the same numerical value on either side, just in slightly concealed formation. So why is identity useful? Let me give you a run-up for it. Let's start off with a very simple little symbolization key. Let's have the domain be people, and let's have the two-place relation, one hates two, and we'll have little c be Scrooge. Everybody knows Scrooge, right? Christmas story. If you guys haven't seen the Muppet Christmas Carol, you should fucking get out now and go watch it. Like, better use of your time. But, okay, using this key, how would we say Scrooge hates everyone? HCX. Nice, right? Scrooge hates everyone. Now, notice, if Scrooge hates everyone, who is one of the people that Scrooge hates? He has to hate himself because he's in the domain, right? So how would we say Scrooge hates everyone else? How would we say Scrooge hates everyone who isn't Scrooge? Note, strictly speaking, up until one slide ago, we didn't have the tools to say that yet. We might want to say Scrooge hates everyone else. Scrooge hates everyone other than Scrooge. Or Scrooge hates everyone except himself. Now that we have the identity predicate, we can say how that is going to work. We're going to take that same sentence, the universal, right, that says Scrooge hates everyone, but we're going to add another clause. And we're going to say Scrooge hates everyone who isn't him. That is, it's not the case that X is identical to Scrooge. So by denying the identity relation, we guarantee that Scrooge hates everybody else. Again, it'll be easy when we see it. We can say everyone who isn't Scrooge is hated by Scrooge, i.e., everything that is not identical to him is a target of his hate. So again, what does this first clause say? It is denying that the identity relation holds between our object X and the thing named by C. Something to note here, right? An important grammatical thing. When we deny an identity claim, we always put the negation in front. We don't put a line through the identity. We never put an identity back here. Because this is just another relational claim. It's a bit like saying it's not the case that Scrooge loves this person. You always put the negation in front of the relational predicate. Well, in this case, since we write it in the middle, we put it in front of the first name. All this tells us is it's not the case that the identity holds. That first clause, the antecedent. And the whole sentence says, hey, for everything in the domain, if it's not Scrooge, then our boy hates it. Yes? Good, because remember what we want to say here is in this case, for everything that isn't Scrooge, right? So everyone who isn't Scrooge is going to be hated by him. By using the universal and the conditional together, right? Because remember, it's still embedded inside this conditional structure. We're saying, cool, you can dig through the collection of people, pick every single person. As long as you didn't grab Scrooge, antecedent's true, and then we're off and running. Nice. Nice. Okay, so identity lets us start talking about when things are different. It also lets us start talking about when things are the same. And in fact, what we're going to do now that we have identity is we can capture a bunch of really useful counting expressions. But let's run through some other ones, right? So identity is helpful with other sentences. This is basically the same, but I've added two names. Does everybody know who Bob Cratchit is? He's kind of, other than Scrooge, the main character. He's the accountant who works for Scrooge. He's played by Kermit in the Muppet movie, if you haven't seen it. And Tiny Tim is, of course, Bob's little son who melts Scrooge's heart, blah, blah, blah. Doesn't really matter. But we can use identity to express other things. So if we wanted to say, no one besides Scrooge hates Bob Cratchit, how would we say this? No one besides Scrooge hates Bob Cratchit. Well, we can literally hear this as, it's not the case there's someone who's distinct from Scrooge that hates Bob. We could just read it as, there are no non-Scrooges that are Bob haters. So we can read it like that. Not the case, there's something in the domain that's distinct from Scrooge and is a Bob hater. And similarly, if we wanted to say only Scrooge hates Tiny Tim, well, this is kind of similar to one of the ones we did in the homework, right? Remember, only dogs like samurai movies? So if we read this one, only Scrooge hates Tiny Tim. If you're a Tiny Tim hater, who do you have to be? Got to be Scrooge. So for everything in the domain, if you're a Tiny Tim hater, cool, you must be identical to Scrooge. Again, we're moving kind of quickly because this is just embedding the identity predicate in sentence structures we've already done. So let's look at some other sentence structures that we can kind of get. Okay. Yes, please. Exactly. That's good. Because of course, right? We've got two different ways to say none. Which I'm very happy that we captured, right? Nice. Again, the important thing here, though, is that we can start to see how we embed these identity claims. Use them to say only or none or everyone except. So, let me talk to you about one of my very favorite subjects, beer. Put that down while I'm talking. Right. So, let's have our domain be universal, and let's have our predicate be is a beer. Now, suppose I wanted to say that there's at least one beer in the world. There's at least one beer in the world, thank God. How would we say there's at least one beer? Well, let's think. Do we have a tool that lets us say there's at least one? What is it? It's the existential, right? So how could we say there's at least one beer? There's at least one thing in the domain that is a B. Now note, what does at least say? At least sets the floor. It sets the minimum. There's at least one. There's, thank God, lots more than one. But the sentence tells us there's at least one. The floor number is one. Now, how would we say there's at least two? Now we're really talking. How would we say there's at least two? Well, the most obvious move we'd make, right, is to have two existentials. Let's have existential X and existential Y, and let's say X is a B and Y is a B. But this doesn't get us at least two. Why does this not get us at least two? Why does this not guarantee that there is at minimum two beers in the world? To see the problem here, again, we can think metaphorically. Take our existentials as the sort of cranes in the grabber game. This tells us there's two grabber arms. And this says, hey, there's at least one thing in the domain that crane X can grab, that's a B, and there's at least one thing in the domain that crane Y can grab, that's a B. But why does this not guarantee that there's at least two? They could be grabbing the same lonely beer. Nothing is preventing them from both latching on to the same thing and bringing it up. This is a really important conceptual point. Different quantifiers does not automatically mean different objects used. You can plug the same thing in for X and Y. So how are we going to change this sentence to guarantee that we get something different? Yes. So we need to add another clause. We need to add another clause that tells us, hey, whatever you grabbed are not identical. So we could, so far, grab the same thing twice. That would be very unfortunate. Instead, what we do is we add a clause. We say, hey, and it's not the case that x is identical to y. And what this clause does is it guarantees the crane that's x and the crane that's y have to have grabbed two different objects. Because if they grabbed the same thing, then this clause is false. So, if we want to say there's at least two, we need to have two quantifiers and a clause that says the two quantifiers are grabbing different things. So how do we think we do at least three? Well, if there's going to be at least three, how many existentials are we going to need? Going to have three, right? There's going to be x, y, and z, and they're all reaching into the domain. And they're all grabbing things that are beers. But importantly, we also need to say they're grabbing different things. So we have a clause that says x isn't y isn't z, and x isn't z. And what do these clauses do? They're just clauses that say, hey, each variable is not identical to the other ones. So what are these capturing? They're setting minimum numbers. They're setting minimum numbers. They're setting the floor. You want to have a good time? There's got to be at least 3 beers. At least. Let's hope to God there's more, but that's the kind of floor for a good time. So the trick here, if you have at least n, is you need n number of existentials, and then you need a negated identity clause for each pair to say they're distinct. If there were at least 50, there's going to be 50 existentials, 50 B's, and then a hell of a lot of these negated identities. For every pair, there would need to be a negated claim. I'm never going to ask you a question that crazy. But note how easy it is, at least structurally, to build a sentence like that. It would just be cool. I just need to keep adding more negated identity claims. That's it. The key thing here is whatever number you're talking about, you need that many existentials, and then the clauses to tell you pairwise they're different. Okay, so we have at least. That sets the floor. That sets the minimum. Let's flip it. What if we want to set the maximum? What if we want to set the maximum? What if we want to talk about at most? So at most sets the ceiling, right? It sets the maximum number you can have. This is my wife talking to me. She says, look, if you're going, you can have at most 1 beer, right? There's at most 1. Again, same domain, same basic symbolization key. If we say there's at most 1, there's at most 1. The ceiling is max 1, could be 1 or 0. Let's go with our first one. If there's at most 1, what is there not? Good. So we can rephrase that, right? If there's at most 1, right? If the ceiling is at 1, then where's the floor? The minimum can't be higher than that, right? The minimum could be 0, could be 1. But importantly, if there's at most 1 beer, it's not the case there's at least 2. If there's at most 1, well then it certainly ain't the case there's at least 2. So one easy way to do at most is literally just negate at least 2. If you're doing at most n, then you can say it's not at least n plus 1. Then you only need to know one structure. But we can also do it another way. And this is a little bit clearer for some people. If there's at most one beer, suppose you've got two quantifiers and you reach into the domain and both of them pull out a beer. Both of them reach in and grab something that is a B. If there's at most one, what must they have done? If both cranes come out and say, hey, I found something that's a B, if there's at most one, they must have grabbed the same thing. So we can say, this is just an English version of what I just said. We can say this, for any X and any Y, if we reach in and grab it, and both of them come out as B's, then they must be identical. I must have grabbed the same thing twice. So these are two different ways to give us the max, right? Two different ways to say at most. In this case, at most one. Now, so far so good? Okay? And I know we're hitting you with a lot, but it's no worries. We're going to talk about it more. So how would we say there's at most two? First things first, if there's at most two, what can't be the case? There can't be at least three, right? So, easy peasy first version. Just do the negated at least three. Easy. Now, if we wanted to do it with the universals, how would we do it with the universals? Well, it's the same basic process. If there's at most two, then we will say, hey, if you reached into the domain 3 times and you pulled out what you thought were 3 beers, then either your first 2 grabber arms got the same thing, or your second pair got the same thing, or your third pair got the same thing. Again, that's this in English, but here it is in symbols. For any X, any Y, any Z, if X, Y, and Z are all B's, then either your first 2 arms got the same one, or your second 2 got the same one, or your third got the same one. Note here, the consequent is a disjunction. So it could be that there's only one, and you just grab the same thing 3 times. So the trick for at most, if you have at most n, you always need n plus 1 quantifiers. And then you'll need either clauses, if you're using the universal, clauses that say they're identical, pairwise, or you just use the negated at least 1 bigger. Good so far? So we've got tools now to say, here's the minimum number, here's the maximum number. The next one, and the last one before we take our break, is going to be when we have exactly. So at least gives us the ceiling, at least gives us the floor, it sets the minimum. At most gives us the maximum. Exactly is when we set them to equal. So how would we say there's exactly one? When is it the case that there's exactly one? Let's think. If there's exactly one, what's the minimum number of beers that we could have? Our minimum is 1, right? Our minimum is 1. And our maximum is also 1. So here's the really easy way to say exactly 1. Just take the conjunction of at least and at most 1. Literally. Just take at least and at most and slap a conjunction in between. Boom. Touchdown, Jesus. Now, notably, there's a slightly nicer way to do this, and it's going to be beneficial to get used to the slightly nicer way. The slightly nicer way is going to say this. There is a thing X, and it's a B, and anything in the domain that is a B is identical to it. I'll just give you the symbolization and we'll talk through it. So this one tells us there's at least one thing that's a B. And then this clause tells us, hey, anything, if it's satisfying that same predicate, it must be identical to the X you had before. This is another way to say exactly one. And just for funsies, how would we do exactly two? Bother with the whole thing. But if we think about the general structure, there's going to be two existentials in the front. Existential X, existential Y. X is a B, Y is a B. Oh, hey. And if you grab any third thing that happens to be a B, you must have grabbed X or Y. Again, once you start to see how these structures go, it will just become natural. Lovely. Lovely. Okay. So two ways to say there's exactly one. And we could do exactly two. I just talked you through it. You could do the really hideous one, which, please God, don't do this. This is very horrible and confusing. But note that this is literally just a conjunction of there's at least two and at most two. You can do the simpler one, which is just there's two, they're different, and anyone you grab must be identical to them. I want to stress some things before we go to break, before we move on. Note there are already getting a lot of quantifiers here, right? Don't be put off, because the general process is very straightforward. If you're doing at least n, then you'll need n existentials. If you're doing at most n, then you need n plus 1, whether it's universals or existentials. If you're doing exactly n, then you need n existentials in the front and a clause to say they're all. The basic process is straightforward. If you know how to go from exactly 1 to exactly 2, cool, we're good. Now, again, also want to say, that's a lot of stuff I'm throwing at you, and I know you're tired because you just had a lecture from Michael. No, that's not true. Michael's a genuinely lovely, excellent teacher. I just like to tease him. Dude, I was looking at the camera. So, what I want to do, we're going to take our break now. And when we come back from our break, we're going to take the stuff that we've just talked through, and we're going to use it to talk about, if you remember right when we first started FOL, I told you about another way to pick out individual objects. We're going to use the machinery we just did to define definite descriptions. So it's 34 right now. Let's take a break to 45, so 11 minutes or so, and we'll come back and go from there.